This video is going to be a refresher on a little bit about what we learned in algebra on systems of equations. So systems of equations are where we have multiple, in our case, linear equations that are kind of stacked together. So we have multiple lines, and on a graph, if you recall, we'd have something like the green line and the purple line, and we'd have an equation for each of those, and there's some intersection point that we call the solution to the system. So we can use calculators to figure that out, but this year we're not using calculators, so we want to make sure we remember our two methods of solving these systems of equations by hand. One is going to be by substitution, which is where we solve one of the equations for either x or y, and then plug what we have into the other equation. The second way is by elimination, which is where we match up something between the two equations and then add them together to eliminate one of the variables, and then solve for the one that's left, plug it back in to find the first variable, the one that we got rid of. So let's look at some examples. I'm going to just make up numbers, so these probably aren't going to work out very nicely, but we can check and verify them using a calculator just to be sure that it's working out correctly. So let's make an equation 2x plus 4y equals 8. That one's nice because everything's even. And then I'll make another one that doesn't really line up with this one as far as where the variables are sitting. So we'll make this one y plus 5x plus 7 equals 0. So I left this y as a single. Actually, let's make it 3y. We'll make this one terribly ugly, and that one looks nice. So we're going to look at solving this by substitution. Solving by substitution, we need one of our variables isolated. And I see that it would be very hard to get a single y or a single x in this equation, where we have all these different odd numbers that aren't divisible by each other. But in the first equation, I could get this x by itself pretty easily. To do that, I just need to rearrange 2x plus 4y equals 8. I'll start off, since everything's even, by factoring out 2. I'm going to divide both sides by 2 and rewrite this as just x plus 2y equals 4. And then to solve for x, we move this 2y to the other side. It becomes x equals 4 minus 2y. Or negative 2y plus 4 would be the same thing. Now that x is all by itself, we can take this part here, this 4 minus 2y, and plug it in for the x in the other equation. We can't plug it into the one that we started with, because then we're not working with the system and everything will just kind of cancel out and it won't work. We need to plug this into the other equation. So if we'd isolated the y or x here, we would need to plug it into this one. So let's do that. We're going to do 3y plus 5 times, and then we're replacing x here with 4 minus 2y. And then we continue with what we had there, plus 7 equals 0. And now our goal is to solve this equation for y, because it only has y as a variable. We need to distribute this 5, so we get 3y plus 20 minus 10y plus 7 equals 0. And now we need to get the constants over to the right side. So if I collect my like terms, I get negative 7y from 3y minus 10y, and then 20 plus 7 gives me 27. Then I need to have the y's and the constants on opposite side. I like to keep everything positive, so I'm going to actually move the 7y over here and get 27 equals 7y. Then to solve for y, we need to divide both sides by 7 and get y equals 27 over 7. And like I said, I made up some bad numbers, so it was going to look bad, but that's what our number is. So we know y at this intersection point is 27 over 7, but we don't know the x value at the intersection. So we need to take this 27 over 7 and plug it back into either of the two original equations. I'm going to go with the top one just because, again, the numbers aren't quite as ugly, but all these numbers are going to end up being ugly in the end. So if I plug in 27 over 7 for y right here in the top equation, I get 2x plus 4 times 27 over 7 equals 8. And this is going to tell me the x value at the intersection. So what we're solving for in all of these is an ordered pair. So 4 times 27 over 7, that doesn't simplify at all. So we just have 2x plus 4 times 27 is going to be 8 to 108. So 2x plus 108 over 7 equals 8. Then I need to combine my constants. So I'm going to move the 108 over 7 over to the right and get rid of that and have 8 minus 108 over 7. To combine these into a single number, they both need to be over 7. So I can rewrite this 8 as an something over 7. To do that, I multiply the top and bottom by 7. So we take 8 over 1 and multiply by 7 over 7, and that becomes 56 over 7. So I have 2x equals 56 over 7 minus 108 over 7. So that's 2x equals 56 minus 108 is negative 52 over 7. Then I need to divide both sides by 2. When I divide by 2, remember that's the same as multiplying by a half, if you want to think of it that way. That could make working with these fractions easier. Our half and our 2 cancel, and we get x equals negative 52 over 14. So you could also think of it as dividing by 2, in which case we would divide the 52 by 2. So here we have an even number over an even number, which we can simplify. So we'll write this as x equals negative 26 over 7. So 7 doesn't divide into 26, so that is where x is. So our answer to this, the x-coordinate is negative 26 over 7, and the y-coordinate was at 27 over 7. So our intersection of the two lines here should be somewhere in quadrant 2, so it should be about here. Let's go ahead and graph this and see if it looks like what we came up with. So we have 2x plus 4y equals 8. That's our first equation. Our second equation was 3y plus 5x plus 7. 3y, 5x, 7 equals 0. 3y plus 5x plus 7 equals 0. So our intersection is at negative 3.7, positive 3.8. And if we were to put that in a calculator, so 7 times 3 is 21, plus we have less than another 7. So, and this is almost 4, because 7 times 4 is 28. So that seems like a very reasonable approximation that it would be 3.7 and 3.8 for those. We could type those fractions in a calculator if we wanted to verify that they're exactly that, but I'm confident those are correct. So that's how we solve by substitution. Even when we don't have a calculator and the numbers end up being terrible, we can still work it all out by hand. It's not that big of a deal. It just takes some basic algebra skills of manipulating these numbers. So our second method is elimination. Let's make some room here and look at how we could solve one of these by elimination. I'm going to make up another system. We'll do 2y equals 5x minus 7. So we're going to keep some ugly numbers in here, probably end up with some bad looking results like we had before. And then let's do 3x plus 4y equals 9. Just making up numbers again. So in elimination, we do that when it's not easy to get a single x or y by itself. So here, this 2y, 5x, none of these are easy to isolate a single x or y. So to do elimination, we need to make sure the two equations line up with the same variables in the same places. So my first problem here is my y and x are on opposite sides here, and they're on the same side here. So to make these kind of look the same, make them parallel structures, we're going to make this 2y equals 5x minus 7, and here we're going to send the x's over to the other side so that it looks like this. So we'll get 4y equals negative 3x, because we subtracted 3x from both sides, plus 9. Now these line up. To use elimination, we need one of the variables to be equal and opposite of what it is in the other equation. So in this case, I have 2y and 4y. I picked this on purpose so I knew I could multiply by like a whole number and not have to use fractions here. So 2y and 4y, if I want those to be equal and opposite, I could multiply this top equation by negative 2. Rewriting it, that would give me negative 4y equals negative 10x plus 14. So I'm just distributing this negative 2 to everything in the equation. So I'm not changing the equation, but I'm just scaling it up. It's still the same equation. But now this negative 4y and this other equation's positive 4y are equal and opposite. What that means is I can just add these two equations together, kind of like old school addition, and do negative 4y plus 4y equals 0. That's going to be equal to negative 10x plus negative 3x. That's negative 13x. And then 14 plus 9 is 23. You can also do this by subtracting the two equations if the two terms are equal and not opposite, but it's a lot less confusing to add them together. So it's generally better to make it equal and opposite and then add the two equations. It'll help you not make little mistakes. So now I want these two to be separated so I can solve for x. So I'm going to bring the x's over here and they become positive. 13x equals 23. And then divide by 13, and as promised, we get a really ugly number. X equals 23 over 13. Now we know that that number is bigger than 1, but smaller than 2, because 2 times 13 would be 26. So we're expecting our x-coordinate to be positive 1 point something that's a little less than 2. So we'll say that's about 1.8 maybe. We'll verify that with the calculator, but we can also just leave it as a fraction just so that we kind of understand what number we're talking about. It's about that much. So now we're going to plug that back in to one of the original equations. I think that it'll be easiest to plug in, it's not going to be easy in either of them, so I'm just going to pick this one and plug in the x's here. So I have 3 times my x value of 23 over 13 plus 4y equals 9. So now we can solve for the y coordinate of our intersection. So 3 times 23 over 13, that's not going to simplify. It's going to give me 69 over 13 plus 4y equals 9. Then we're going to subtract this fraction from both sides. 4y equals 9 minus 69 over 13. We need to multiply this 9 by 13 over 13 so that it becomes, so we can combine it with this one. So 9 times 13, we get 27, and so that's 9. I should stack it the other way, it's easier for me to think of. 13 times 9, 27, and then 11, so 117, that sounds right. So we'll rewrite this 9 as 117 over 13. Okay, so then we can add these two together and get 4y equals 117 minus 69 would be 48 over 13. and then we need to divide both sides by 4. So when we divide by 4, this 48 will become 12. So y equals 12 over 13. So our intersection should be at 23 over 13, comma, 12 over 13. So we know this one is a little less than 2, and this one is just a little less than 1. So we expect the intersection to be at around like 1.8, 0.9, something like that. So let's go graph this one and see if that's where it comes out. So we have 2y equals 5x minus 7. 2y equals 5x minus 7. And then our other one was 3x plus 4y equals 9. And our intersection is at 1.77 and 0.9. So again, a little less than 2 and a little less than 1. So pretty much exactly what we had calculated here. So that was just a refresher of two things. One, that we can use these two methods of substitution and elimination to solve systems of equations by hand. The other being that it doesn't matter if the numbers come out nice and even or if they come out to be these horrible monstrosities that are fractions. We can solve them and work with these fractions, no problem. It's not a big deal.